When an industrial evaporator is running at full capacity, operators face an immediate problem. You need to know exactly how thick the liquid has become, but the entire process is sealed inside a massive churning steel tank. You solve this by measuring the boiling point elevation, or BPE. It is the most reliable, measurable indicator of brine concentration available to an operator. Today, we are going to calculate your exact BPE using the plant operational method. We will do this in 4 precise steps, using the live conditions right off your plant floor. Before we start, you need 3 tools: access to your evaporator's live gauge readings, a standard saturated steam table, and a calculator. This entire process relies on one standard formula. BPE equals the temperature of your boiling brine minus the boiling temperature of pure water. Using live operational data for this equation prevents critical errors. It forces you to rely on the actual, real-time physical state of your plant, rather than theoretical design parameters. Step 1 begins at your control panel. We need to document the exact thermodynamic reality of your system right now. First, locate the gauge tracking the actual, live temperature of the boiling liquor inside the evaporator. This gives us our first variable, T brine. Let's establish a baseline. T brine at exactly 106.5 degrees Celsius. Step 2. Secure your vapor pressure. Check the gauge monitoring the evaporator's vapor space. Pay close attention to units. Record absolute pressure, or bara. Our example reading is 1.05 bara. You now have your live brine temperature and your live vapor pressure. These 2 numbers form the unarguable foundation of the calculation. With the live data secured, we step away from the control panel and open our saturated steam table. This cross-reference grid dictates what temperature pure water boils at under our live pressure. Scan the left column for our recorded 1.05 bara. Follow that row right. At 1.05 bara, pure water boils at 101.21 degrees Celsius. This is our T pure water variable. Occasionally, your live pressure reading will fall between the rows on this document. If your gauge reads 1.08 bara, you won't find it explicitly listed. This chart maps the solution. When a number is unlisted, operators use mathematical interpolation, mapping a steady line between the 2 nearest known values to pinpoint the exact temperature in the middle. The steam table translates a live physical pressure into a baseline theoretical temperature, giving us a perfect point of comparison. Now for step 4. This is where we combine our live gauge data with the theoretical steam table data. We return to our standard formula, BPE equals T brine minus T pure water. Drop in the recorded values. Take our live brine temperature of 106.5 and subtract our pure water temperature of 101.21. The math gives us a final value of 5.29 degrees Celsius. That single digit is your definitive answer. It represents the exact temperature difference caused entirely by the dissolved solids suspended in your system. You have successfully calculated a BPE of 5.29 degrees Celsius. Now we apply it. A value this high physically proves that the brine inside the evaporator is heavily concentrated and carrying a massive load of solids. This graph plots typical BPE values over a shift. As the BPE number rises incrementally over time, it confirms that your brine is becoming progressively thicker. Take your final calculated number and log it immediately in your shift records. Make this process a habit. Repeating this method at regular intervals provides a clear, ongoing assessment of your evaporator's mechanical health. By pulling live temperatures, checking your vapor pressure, referencing your steam table, and doing the math, you convert raw gauge data into actionable intelligence, keeping your ZLD system safe and efficient.